Alright, today we're going to be talking about, or in this lesson, talking about sequences as functions. And are essentially patterns. And if you recall from elementary school, this is the type of pattern you might be looking at to determine what comes next, a big apple or a small apple. So hopefully you can determine what the pattern is and notice that a small apple comes next. Here are a few more to determine. So of course here we've got a cloud that would come next, a dog that would come next, a pine tree, and in this case a sun. But we're going to look at specifically sequences that are numerical, not pictorial. Alright, so we're going to look at sequences, numerical sequences, and when we talk about a sequence, these each are terms in my sequence. So this is the first, second, third, fourth term, and then of course these dots mean that it just continues. Sometimes these are referred to elements or members, but most often terms in my sequence. A sequence is obviously an ordered list of numbers. We've already said that. But the numbers that are in that, or the terms that are in my ordered list, are determined by a formula or by a rule. So I can evaluate by plugging in 1 to find the first term, plugging in 2 to find the second, 3 to find the third, and so forth. If I typically have a function, like let's talk about a linear function, I can have values in the domain that are negative infinity to positive infinity. But in this case, my values in the domain are not going to be that. They're only going to be the natural numbers, which start with 1 and count up by whole numbers, because when I'm talking about the terms in my sequence, let's go back here, I have the first, second, third, these 1, 2, 3, 4, these are the values in my domain because they're the values that I'm plugging in. The first term I plug in 1, the second term I plug in 2, and so forth. So I can't plug in non-whole numbers and non-positive whole numbers because it's not possible to have a term that's term number 1 and a half. So it's got to be term 1, term 2, term 3, and so forth. These numbers are from the natural number system, and they are what we use to count. So if I asked you to start counting, naturally you would count starting with 1, 2, 3, 4, and so forth. In this case, each sequence is going to be a discrete function because it's just going to be single values, not continuous, because it has to be at 1, at 2, at 3, at 4. It's not going to be between 1 and 2. Some key concepts that we're going to talk about. When we talk about sequences, we can talk about an explicit formula and a recursive formula. And the explicit formula is helpful because I can find a specific term in my sequence. So if I'm looking for the 9th term, all I have to do is plug in 9 into the explicit formula and it'll give me my answer. The recursive formula is used to only find the next term in a sequence. So if I want to find the 9th term, I have to know the 8th term in order to do that. Alright, so the two types of sequences that we're going to talk about are arithmetic and geometric. Arithmetic sequences have a common difference because it's a number that I am adding every single time or possibly subtracting. So to find the next term, I have to see what have I added to get there. I could have added a negative number, which essentially would be subtracting. It's going to be a constant common difference. It's the same thing every time. If it's not constant, then it's going to be a common ratio. and that would mean I'm multiplying by something every time, so the difference between each term wouldn't be constant like this. So let's look at it a little bit more closely. When I graph sequences, remember that they are discrete, so we would not connect them in any way. Alright, so when we use the recursive, the idea of recursion, remember I have to use the term before it to find the next term. So if I look at these first couple of terms, I'll see that the common difference is 4. I'm adding 4 every time. So to find the fifth term, I'd simply add 4 again, keep adding 4, and then this one will be 41. Same thing here. Notice my common difference now is 5. So I've got 28, 33, and 38. For this one, you'll see it's not a common difference. Here it's 12. Here it's much more than 12. So I see, okay, well, if there's no common difference, then what's the common ratio? So 6 times 3 gives me 18. 18 times 3 gives me 54, and so forth. So to find these terms, all I would have to do is multiply by 3. And honestly, I don't have a calculator with me, so I've got 162. Whoop, darn pen. 162 times 3 gives me 6. 486. Is that right? And then I could keep multiplying by 3 to find the successive terms. In this case, it wants me to find the first 5 terms, graph them, and then find the 9th term. When I'm given this formula, I can specifically just plug in values to find each one. So to find the first term, remember this is an explicit formula, so I can just plug in and I get 3 plus 1 is 4. So my first term is 4. To find the second term, I can plug in 2. 6 plus 1 is 7. So my second term would be 7. To find the third term, 3 times 3 is 9. 9 plus 1 is 10. So the third term would be 10. And you'll notice now my common difference is 3. So to find the next term, I could just add 3. The next term, I could just add 3. And you'll notice that these make a linear graph. So whenever my function is arithmetic, it is represented by a linear function. Oh, I forgot to find the 9th. Whoops. So if I wanted to find the 9th term, again, I could just plug in 9. 3 times 9 plus 1. This darn pen. 3 times 9 plus 1. So 28 for the 9th term. For this one, you'll notice it's not linear. So let's start plugging in values again, finding the first 5. 1 minus 1 is 0. Anything to the 0 power is 1. So 3 times 1 is 3. So my first term is 3. My second term, 2 minus 1 is 1. 2 to the first power is 2. 3 times 2 is 6. Find my third term, so my first 2 terms, the first term is 3, my second term is 6, my third term is 2 squared, which is 4, 4 times 3 is 12, so you'll notice from here to here it doubles, and from here to here it doubles, so I've got a geometric sequence because it is multiplying by a common ratio. So my third term is 12, and then you'll see if I double that, I get 24. If I double that, I get 48. So you'll see that that is represented by an exponential, and that matches my exponential here. These are my, again, a recursive because it has this. This here basically is representing or asking or telling you it's the term before. So for example, if I want to find the fourth term, which is what they're asking me to find, then I would need to know the fourth minus 1, so the third term, and then multiply it by 2. But I don't know the third term, I only know the second term. So to find the third term, I could use the second term times 2. Again, second term times 2. So second term was 6. 6 times 2 is 12. So the third term is 12. Now I can find the fourth term by doubling it. And the fourth term is 24. Same idea here. If I want to find the fourth term, and this should be a with a little 4, a sub 4, like a subscript. So again, to find the fourth term, I would need the third term plus 7. But I don't have the third term, I only have the first term. So I'm going to use the first term to find the second term. 10 plus 7 is 17. That would be the second term. To find the third term, it would be 17 plus 7. So that would be 24. And then I can plug that in here. 24 plus 7 is 31. Barron is on a nature hike. He starts out in a valley and climbs up a hill, stopping at regular intervals to take pictures. The elevation of the land in feet below or above sea level at which Barron stops follows the function. It gives you this function that's recursive. This is the recursive formula. The first place Barron stops to take a picture is 4 feet below sea level, so a sub 1 equals 4. And actually, I would argue that it should be negative 4 because it's below sea level. So if the first stop, we're looking for the 6th place he stops. So his first stop would be just by plugging in my A1, which is 4. Actually, to find his second stop, I'm sorry. His first stop is at negative 4. Then I would plug in negative 4 plus 5, so his second stop is going to be at 1 foot. His third stop would be at 6. Fourth stop would be at 11. Fifth would be at, remember, see, I'm just adding 5 every time. Fifth would be at 16. And sixth would be at, 5 would be at 21. So his sixth stop would be at 21 feet above sea level. These next couple of examples are from the EOCT review guide. So these are some examples of how you might see functions on the EOCT. In this sequences on the EOCT. In this sequence, the first term is negative 1, second is 1, and so forth. So this is my domain and this is my range. To figure out which function represents this sequence, all I have to do is plug in my x values to see out which one gives me the correct y values. So if I plug in 1 here, 1 plus 1 is 2, and that's not the y value that's matched with it. Plug in 1 here, 1 plus 2 is 3, not it either. Plug it in here, 1 times 2 is 2, 2 minus 1 is not negative 1, but you'll see this one works. And you may get one that works, 2 that work for this first one, but you need to keep testing to make sure. But in this case, this is the only one that works for the first one and for any of the others. Same idea. This one, I'm plugging in x value, see which one gets out the correct y value. So if I plug in 1, 1 plus 7 gives me 8. However, if I plug in 2, 2 plus 7 does not give me 11, so be careful with that. If I plug in 1, 1 plus 9 is not 8, so that one doesn't work. But notice it does work for the second one, so be careful with that. The answer choice C, 2 times 1 is 2, 2 plus 5 is 9, so that's not going to work. And then, let's try it again. 1 times 2 is 2, 2 plus 5 is 7, so that's not going to work. And then this last one is the one that works. I plug in 1, 3 times 1 is 3, 3 plus 5 is 8. 3 times 2 is 6, 6 plus 5 is 11. So all of these x values, when I plug them in, give me these y values. Same idea, and actually these two are exactly the same, but you'll see I'm plugging in d values to get out c, and you'll recognize that this is my correct answer. Last one, it's asking me, okay, if I plug in f of 12, and this is what my plugging in looks like, what's f of x? Well, before we replaced x with 12, so now we're just going to go back and plug in x is here, so which one matches what I have?